Awesome.
Recording has started.
Welcome everybody to another one of our PFTC webinar meetings. Today we are pleased to have Dr. Sharon B. with us. She'll present us her latest research on harnessing Midfield Game and physics-informed deep learning for emerging transportation modeling. Sharon is an associate professor in the Department of Civil Engineering and Engineering Mechanics at Columbia University in the city of New York since September 2016. Before joining Columbia University, she was a postdoctoral researcher at University of Michigan Ann Arbor Transportation Research Institute, and before that, she received her PhD from the Department of Civil, Environmental, and Geoengineering at the University of Minnesota Twin Cities in 2014. Dr. D has received several awards, including the prestigious NSF Career Award and some other awards from TRB. And so with all that said, the floor is yours, Sharon.
Yeah, thank you, Ralph, for the nice introduction. So I'm Sharon D, so I'm here virtually to share my work. And also, I would be happy to hear back your opinions and or suggestions from the review flow community. And this is the joint work with students, Xuan and my previous postdoc, Dr. Rongye Shi, and also two professors, Qiang Du from Math Department and Xi Chen from Computer Science. So first I want to talk about mixed autonomy. Basically, it's the area people define as the mixed traffic comprised of autonomous vehicles and human drivers. And the normal practice is to model autonomous vehicles, or we call the AV, as a control agent. So what I mean by control agent is they move as like automated and driven by some physics or by some rules, like car following models. However, let me show you a video. Probably most of you have seen it. So it's some clip, a short film from the tweets people uploaded. So this is probably in California, and then one guy is driving on highway, and he reached to the mainland, and he saw a Waymo car in front of him. Sorry, let me play it. So you can see actually the Waymo car has its the turning signal on, the blinkers on, and it tries several attempts to merge in. But even the car that filming the Waymo car successfully merged in, but Waymo car couldn't find any opportunity, and then it had to leave off the highway from the next off ramp. So then why this happens, we feel like one reason is probably now if you go to YouTube, you'll see many people from California and Arizona share the video about how Waymo in a weird way. So then people develop this sense that when we see Waymo car, we don't want to cooperate. So nobody slows down, and then they don't create enough gaps for the Waymo car to win. And another reason is from a human's perspective, we are proactive. We're anticipating what may happen in the future. Even as a conservative driver, but if I see that I'm approaching the end, I may ask myself this question: shall I force in? Then my behavior may suddenly be elevated to aggressive driving. Then in that case, then I will be able to move in. But for Waymo car, apparently it like has a constant program in driving this car that we don't know, but it seems it's a little counterintuitive. So that's why we are thinking maybe in the future, if we have level 4 car who want to drive in this mixed traffic. Instead of assuming that these cars are control agents, we want to say whether they should be artificial intelligence driven agents. So what we mean by AI agents is they are rational and they try to optimize some utility function pre-programmed into the car. And they are either cooperative or non-cooperative agent with the neighboring cars or with some other autonomous vehicles. And then they should have this learning and adaptation behavior because the travel environment is of human drivers is highly stochastic, it's even unpredictable. So they need to pick up this learning capability. And I believe that in the future, on the public road, when we have the mixed traffic with AVs and HVs, the human-driven vehicles, this become a battlefield. And we need a game theory to really empower the driving intelligence of the autonomous. In this talk, I would like to bring up three areas we are working on right now. So first of all, we try to use the game theory and also dynamic control and machine learning to solve the challenges we are facing now in this mixed autonomy. For the first topic, our question is what are the best or optimal driving strategies for AV to navigate the traffic environment. And I will talk about a new concept we borrowed from game theory, the actually emerging concept called Midfield Game. How we develop Midfield Game to power the driving of the autonomous vehicles. Then for the second topic, we'll briefly touch on then how we can leverage the autonomous vehicles that are designed by Midfield Game. For mixed, we will talk about the stability of the mixed traffic. And for the third topic, it's probably a little detached relatively from the perspective, so-called physics-informed deep learning. Okay, I will, in the start of the talk, I will describe this slide. So we will start from the N-car differential game. There's always something. In this game, we focus on ring road and we try to control autonomous vehicles, especially their velocities. And then our question, what are the optimal controls for an AV? To do that, we define the objective function for each AV, and we call the J. It's composed of two parts. The first is the cost function. It can include any terms, including running cost, congestion cost, safety, or even emissions. And then the second one is the terminal cost. Basically, at the end of the time horizon big T, what's the cost we want the car to achieve? This is the setup for the optimal control for each car. But if there are many cars we have to control, our question is, what if everyone solves optimal control problem while others are doing so simultaneously? And then it becomes a game we call the differential game. And in this game, we are interested in so-called Nash equilibrium, which is the equilibrium velocity we want to solve for each car.
Recording has stopped.
Okay, why is the recording stopped?
No, it was the Blue Jeans meeting. That's fine. The Zoom meeting is still recording.
Oh, but is it still ongoing?
Yeah.
Oh, okay. Okay, good. Then at the equilibrium, everyone trying to find its optimal velocity while others doing so. But at the equilibrium, car I's cost should be the minimum while others action holding fixed. So this is a neat problem, but when there are more and more car AVs are put to road, then the question is how do we solve this equilibrium with such a curse of dimensionality? And then our contribution is we try to propose this using the Midfield game to control many cars. And it turns out this becomes like a new traffic flow model. So let me first talk about the Midfield game. So it's basically Midfield game models a multi-agent dynamic system when the number of agents goes to infinity or it's very large. It's essentially a dynamic Nash game with an n-player limit. So the Midfield game was introduced by two groups of researchers back in 2006 and 2007 independently, and it has been so far very successful in interpreting some natural and also the human world phenomena. For example, like Mexican wave or the fish schooling. So the key of this game is it can start from modeling the agent dynamic and then scale it up to the mass dynamic using macroscopic models. So then how do we apply this Midfield game concept to traffic flow to control the autonomous vehicles? So here is the approximation we try to apply. So you can imagine in this system when the number of cars increase more and more. So the objective function actually, we can remove the index I. And the cost function, the first term F, instead of depending on one car's velocity and all other cars, now it depends on the velocity and also the density in the neighborhood. And when we apply this approximation, then we don't see individual car. Instead, we look at a generic car. Here, we remove the index I for this green car. And this car doesn't see individual car in its neighborhood anymore. Instead, it can only see the traffic density. And then it try to control its speed according to the density. And we define so-called Midfield equilibrium, which contains two fields. One is the velocity fields and one is the density fields. Then how do we solve this Midfield equilibrium? So we use so-called forward-backward structure. Let me start from modeling agent dynamic. So when we look at the generic car movement, so this car, as we introduce it, try to solve some, minimize some cost functional. And then when we apply the Midfield approximation, then it's just minimize a generic cost function J, which depends on both its current speed and also the velocity, the traffic density. And given the traffic density is known, then we can solve this agent dynamic. Then in return, we update this velocity field and feed it back to the mass dynamic. Then we solve this flow conservation equation that will give the updated traffic density. Then we can do this process iteratively until the equilibrium reached where the mass dynamic is consistent with the traffic density perceived by the generic car. And we call the agent dynamic the HJB equation is solved backwards because it's still an optimal control problem. And then the mass dynamic is characterized by the flow conservation equation. And it's more generically, it's the FPK equation if we consider stochasticity. Then it's solved forward. So we solve this backward and forward equation until a fixed point is reached, then we will get our equilibrium. So I will skip the detail of how we solve it, but I want to present the results. So we try to compare the autonomous car powered by the Midfield game and also by the LWR model and try to see the difference. So again, we define some generic cost function, but then for LWR, we found out actually it's equivalent to a specific Midfield game with this cost function. And it means that the car try to adjust the speed towards the equilibrium speed And we assume here it's the equilibrium speed is defined by the Green-Shield fundamental diagram. Then centering around this model, we try to develop our own Midfield Game model by adding an additional term. So this is rho J is the jam density, rho is the density, and this term means the car not only try to adjust their speed towards equilibrium, but also try to avoid crowds. So you can think this as a traffic, like a safety term. And then now I will show you an animation on the bottom, and let me explain the figure first. So the in this figure, the x-axis is the space from 0 to 1 on a ring road, and the y-axis we have two lines. One, the blue line is the density, and then the red dotted line is the velocity. You can see Midfield Game and LWR for the upper one, the ring road, we first saw a continuum equilibrium, but then we discretize the equilibrium, try to, for better visualization, you can see how cars are moving and how shock wave actually is dampened. Let me play the animation. So they start from exactly the same initial traffic density, but you can see very quickly the Midfield Game, you don't see the congestion anymore. Cars, the traffic state converge to the actually uniform flow very quickly. But on the right-hand side, you can see for the LWR, the shock wave gradually forms. We found out well in the comparison that, let me go back. So first of all, the LWR actually is a specific Midfield Game with a nicely designed cost function that drives every car move towards equilibrium speed. And second of all, actually LWR is also myopic Midfield Game with generic cost function, which means because for Midfield Game, we look at a long time horizon from 0 to big T, but if we shrink that time horizon, then it will converge in a limit sense to the LWR. So this is our finding, and we also plot this relationship between density and flow. For Midfield Game, you can see the blue line, the blue dotted line is the Green-Shield's fundamental diagram. The black dotted points are measurements from the Midfield Game. Sorry. And then it's like a flower-like. So whatever state you start from outside of the Green-Shields, it eventually, the Midfield will drag it back to the Green-Shields curve. So this is our finding. But actually, this density and the traffic flow has a complicated relationship. So because they are not only depends on the current density, they select their speed based on the prediction of the future density. So that's why this fundamental diagram looks a little messy. So any questions here?
So did you say that it converges, the Midfield Game converges to the Green-Shield?
Yeah, from the when after it reaches the uniform, so I can drag it to the end of the animation. So you can see actually here, on the bottom, yeah, the blue line and the red dotted line for left-hand side. So they will converge to the Green-Shield. The reason is because the cost function we designed for the Midfield is actually centered around this LWR function form.
Very interesting. Thank you.
Okay, thank you. So let's move on to I just talked about how we use Midfield Game to control autonomous vehicles. The next is in the mixed traffic, how we can leverage this kind of controller to stabilize the traffic flow. So let me first define the mixed traffic. We control the AV using the Midfield Game on the right-hand side, left-hand side, and then the HV using ARZ model. which are a second order traffic flow model. The reason we use ARZ because it can have the stop and go wave, and we want to see whether Midfield Game can stabilize those waves. And the state of this mixed traffic system is the density and velocity for each class, the AV and HV. And the flow is the flow conservation equation. And we assume the sum of these two types of cars is equal to the total density. And for Midfield Game, the dynamic equation is the HJB equation we defined before. So here you can see we introduce an actual term beta times rho HV divided by rho J. So this is an interaction term. We assume the AV can also somehow be connected to recognize the density of the HVs. But for HV, we just use the regular ARZ model with this momentum equation. And we assume human driver can only observe the total density in their neighborhood. And here's our results. Yeah, before that, let me clarify the stability. What we mean here is when we perturb the initial density and how that perturbation may evolve as time goes on. And by stability, it means it will gradually converge to the uniform flow. So this is a coarse definition of stability. And then for this figure, basically, we gradually increase the AV penetration rate along the x-axis. And the y-axis is the normalized total density. So the right crosses represents the unstable field, and the blue dots are the stable fields. So let me just pick one, which is when we fix the total density as 0.4, and then we assume there's no AV. So it's a pure HV scenario. So then you can see that we plotted the density evolution. And we initially we deliberately select some bell-shaped density profile, and gradually as time goes on, shock wave will form. So then we introduce 30% of the AVs, and then this is the result. So AVs are driven by the Midfield Game. So you can see the stop and go wave doesn't exist, and gradually the whole system converges to the uniform flow. And we also try to see how we can design the AV controller so that it can stabilize the system better. So then we vary this parameter beta, which is like a sensitivity parameter to represent how AVs react to HV density. And you can see where we increase the beta along the x-axis and also increase the AV penetration rate. So the traffic become more and more stable. So which means the more sensitive that AV is to the HV, then the more stable the system is. So this can provide some guideline for the autonomous controller design. Any questions about this slide?
Do you observe also delay savings, or maybe a greater speed?
Greater speed, you mean like higher than the maximum speed?
No, so the two 3D plots you showed is in terms of density.
Mm-hmm.
What about the speed maybe, or travel time?
Oh, okay. So for travel time, that's a good question. We didn't measure here because the ring road. For the speed, actually it will converge eventually for Midfield Game to the uniform speed for sure. But in terms of travel time, we did this work on a network. We found out it not necessarily minimize total travel time. It really depends on what cost function you pick. For LWR is if you control a car using LWR moving across the network, if you select a different cost function for Midfield Game, LWR may reach earlier or at around similar time. So it depends on the cost function we select and also how much penalty we provide to the to the terminal cost when basically the v function we gave at the the end of the time horizon big T. So if we penalize very heavily, then they were basically forced to reach destination faster. But that's a soft constraint.
Right. Okay. Thanks.
Yeah. Very good question. Thank you. Yeah. So because we have limited time, let me move on to the third topic. So we talk about how we use game theory to control the AVs and how we can leverage it to stabilize traffic. So the next is how we can use this so-called physics informed machine learning to better characterize the driving world that we have now with human drivers. So this machine learning, we usually call it a black box. The reason is because we don't rely on any domain knowledge to discover the mechanism from the data. But from the domain researcher perspective, for example, our traffic models have been developed since 1930s when Green-Shields proposed his model. So then there are millions of models here, and we hope that we can not only use machine learning, but also apply domain knowledge to better train the neural network and help us discover better patterns from the data. Because machine learning alone probably requires a huge number of representative samples. And by applying the domain knowledge that can not only provide some physical constraint that the data have to be satisfied, but also can also provide some insights so that we can use a fewer number of data samples to better train our machine learning models. So that's why we have this so-called physically informed machine learning. But first, let me show this how models connect to each other in this dichotomy coordinate. So the x-axis is the amount of data we use to train a model, and the y-axis is the amount of theory or knowledge we need. For the physics-based models, or we call rule-based models, they highly rely on the amount of information or knowledge we have, but we don't need too much data to calibrate these models. And for machine learning models, in contrast, they require a large number of representative samples, and they don't need any scientific theory or hypothesis. So that's why in the past few years, people start thinking about how we can combine these two and lead to the so-called physics-informed machine learning that can leverage the advantage of both the machine learning and also the existing domain models out there. And actually, this we call the PIML, physics-informed machine learning, have been applied or has been emerging in the past probably 2 years in multiple fields. And there are more and more workshops or conferences that also happening or will happen for different fields. So this is a definite growing area, and I hope by my presenting our preliminary work that can make people get more interested in this field. And so let me maybe just focus on a very narrow area of how this physics-informed machine learning can be used to solve PDEs. Here, I present a very generic PDE form. So the rho is some physical value we are interested in. It can be density field or velocity field. And Nx of rho is a nonlinear differential operator. And then we focus on the time spatial temporal field defined by x and t. And we want to define a residual, which is just the left-hand side of this PDE equation. And our goal is to approximate the analytic solution of this PDE using a deep neural network. And if we can find this perfect neural network, then the residual will become 0. So how do we do that? To train a neural network, the key is to define a loss function. And usually the loss function is defined by the mean square error or some other distance measure that describe how the observed data deviate from the predicted values. But because we add this, we want to add physics, so we will have to add another loss functional term, which is called residual loss. That is defined on collocation points. So I will explain to you what are collocation points. So let's just make it more concrete on this LWR model. We use a simple one, green shields. So the first one is the flow conservation equation. I will explain you why we add a relaxation term here. And then the fundamental diagram is the green shields. And we define some initial condition like initial density and also boundary condition, because we assume the cars are running also on a range road, so it's a periodic boundary condition. And then this LWR model is easy to solve. So this is the density field. And the reason we add this relaxation term is we found out that because this solution contains shock wave, and the neural network is usually will better approximate a differential function. So that's why there's a lot of instability around the shock wave solution. That's why we just add this term to stabilize it. And then we have observed the data. Here we assume we place some sensor, the loop detectors in some fixed location. And then from these detectors, we can observe, given the fixed location and when the time evolves, what's the density in this area. And also we define some so-called collocation points. These are new. These points basically are randomly selected from the XT field. And these points, actually, there's no measurement, no observation. We don't know their traffic density, but assume we know the physics. So then we just randomly select the T, the time and the location points. And we assume we know the physics that follows this known LWR model. And our goal is to train a neural network to see whether we can approximate a solution that is as close to the real analytical solution of LWR as possible. So we define the losses with two terms. The first, MSE rho is the deviation between the prediction and also observed density at those fixed loop detector location. And MSEF is the residual loss. That is the deviation of the prediction of density from the computed density that is calculated from this LWR. So the known physics. Once we do define this loss, we train the neural network, and then it produces a function like this. You can see it's pretty close to the exact solution of the original LWR model. So of course you may say that, okay, because you know the exact physics that generate this data, that's why you can produce such an accurate solution. But how about we don't even know the underlying physics? So that's why then we move on from the LWR model, the data-driven solution, to the real-world data, which is NGSIM. And we use the US 101 data set, which has 45 minutes in the time space, and also 640 meters for total stretch of the road. And we extract the trajectory and calculate the density field, and we treat it as our ground truth. And we assume we place some evenly spaced loop detectors along this stretch of the road. And we try to increase the number of loop detectors. So in this graph, the x-axis is the number of loop detectors. And then the y is the estimation error. Basically, how much deviation our predicted density from the neural network to this exact density we computed directly from the data. And we select several baseline models. So the worst one is the so-called no physics neural network. We only use neural network, it's performed bad. And then we also use the LSTM and the EKF, the Kalman filter. And you can see the PIDL model, we use it's the purple line, which achieved the minimum estimation error compared to other models. Another trend we observe is when we increase the number of loop detectors, basically we have more and more training data. Actually, this performance of these models converge, which means if we have a lot of resources, we don't really need to rely on physics. And this is another figure to confirm our findings. We also increase the number of loop detectors along the x-axis, and the y-axis is the ratio between all the weights between the physics versus the data. So you can see when there are very few data sets, we highly rely on our knowledge of the physics. But if we have more and more data, we rely more on the data instead of the physics knowledge. So that's all about my talk. Thank you very much, and sorry for the inconvenience today.
Thank you so much, Sharon. That was very interesting. Can I start with a question on this slide? So what is the input to your neural net?
Input is X and T. So only the time and the space.
So a single point? No, right?
No, it's for the, probably this slide is better to show. So the it's we gave different X and T from the neural network. The output is it's raw, and the XT should cover the whole domains, the entire time horizon and the entire space we are looking at.
Right, but how would you go about predicting another situation with different boundary conditions, for example?
Yeah, that's a good question. The original formulation of the PIDL for solving PDE, they introduced this observation. You have to observe some initial condition. Mm-hmm. And the boundary condition. If you don't know this is ring road, it's just if it's like a long infinite road with right. On-ramp or ramp, we don't know. Then you have to also use measurements to estimate that. However, in our model, we tried just without using initial boundary condition. But if we have as long as sufficient observation in this XT field, we found out it can actually approximate the solution to a certain accuracy. But if you know the initial and boundary condition, you can further add those into your loss function and to constrain your estimation in those areas, and that will help.
So can you like an example application of this? I'm not sure I understand. So what I see is that, so you have a function that predicts a given day of observation, right? But yeah. what about another day, or how can you use this model?
So this is actually a traditional traffic state estimation problem. So basically, we only assume our observation is only these detectors. Okay. Yeah, we just have fixed the detectors.
Okay, and then so use it for interpolating.
Yeah, exactly.
Okay. All right.
Yeah, so what the training is only those data points along these red lines, and then we try to reconstruct the whole field using those sparse observations.
Right. Excellent. Okay.
Yeah. So basically, we have a lot of traditional model like the Kalman filter and other models to do that. We just say that right. Okay, by adding these collocation points, if we assume we know the physics, that can better do this interpolation.
Very good. So if you have a question, please type it in the chat or unmute yourselves.
Hello, this is Sue. Thank you for the very interesting presentation. I have a quick question. So here you are using LWR model. So it looks like the physics informed part is coming from these collocation points. So
Yeah.
what if you use a different model? And let's say, you know, because even with NGSIM data, people have debates about, you know, which model is best to describe traffic dynamics. So if you don't have full confidence that LWR model is good, and maybe other models are better to describe traffic in this particular section, let's say. So have you played with different models? I mean, how sensitive is it to model specification?
Yeah, exactly. This is a very good point. So we tried the for NGSIM, we tried the green shows LWR and 3-parameter LWR. We also have another conference paper using the ARZ model. So yeah, definitely using the different physics will lead to different results. And also another question is, when you select, even you fix the physics, but you still have to estimate parameter in those physics. So, and we also compared if we do the pre-calibration of those physics before we encode it into the neural network, and we do both the prediction and also the physics parameter calibration all together. We call it parameter discovery, and we compared their performance. Definitely, the latter one is better, but it's harder to train on the neural network. So yeah, I think because this is a relatively new field, I think the most important research question here is, how do you find a good physics that can better represent your data so that it play a positive role instead of actually disturb your prediction and make it even worse. But from this figure, you can see also, if sometimes it's very hard to find a good physics, then the other solution is increase the observation data. Then that the ways that physics play in that total accuracy will be less and less.
Or could you somehow, let's say if you don't have very strong confidence about the model that you're using, I guess, as you said, one way is to have more data, or where you define loss function. I mean, could you weigh the two terms? Is that pretty common to do?
Yeah. So we can also, that's a good question. So we incorporate this alpha, beta, the weights. I can go back to this as also a hyperparameter to tune. So basically here in the loss function, if you add the alpha and the beta, so we also can tune these parameters. So yeah, that's another way to do it.
Okay, thank you so much.
Yeah, thank you. There are some chats.
Yeah, we have a question in the chat.
Sorry, I can't see it somehow. It's my chat box.
Yeah, I can't find it either.
If you can.
I can read a question for you. There are two questions.
Oh, that would be great.
Yes, both questions are coming from Hao Zhou. Hi, Dr. D, very interesting talk. I have a question on the J function you designed for MFG method. Could you explain more how you incorporate density in the cost function?
Okay, so yeah, I can explain it in two places. So one, probably your question is about how this is for the differential game, when we look at individual cars, this cost function f depends on the S car speed and all other speed and position, right? So then when we move to Midfield, there's no position and action of other car. Instead, we replace it with row. So this is the first one, how we remove it basically by using this mean field approximation. When you have the large number of cars, so this you can use this micro and macro link to do the approximation. And then the physical meaning is just the car instead of trying to calculate its own reward function of cost based on all other cars information. Now I only need to focus on the density. So that's the advantage of using this mean field. So another part I want to explain this question is when we try to compare LWR and Midfield Game. So here we add also additional term that depends on role. So this we can interpret as more like a safety cost, soft safety cost. So if you try to minimize this cost, and then turns out basically people, when cars are driving, they try to deviate from this jam density. So in other words, they try to avoid the crowds. Does it answer your question?
Oh yeah, thanks. That's actually my question. So I saw the term it's to avoid the crowd. So a follow-up question is that why the vehicles tend to promote a uniform density in the ring road? But I assume it is to compare to the traditional LWR without the density term here.
Yeah, so that can be another interpretation. Actually,
yeah.
Go
I'm
ahead.
also curious, if not for a ring road, let's say a tangent road, what's the density range does the model need? Like how long does the car need to know the density ahead of it?
Oh, so here actually we assume a predefined time horizon from 0 to rho, the big T. So they try to predict the density evolution all the way to that big T. And if you shrink that T to almost myopic, then we found out that becomes the LWR. So basically, because people use the MPC a lot, so that's actually essentially a myopic Midfield Game. So we assume we look at maybe a very short time in the future, and then we update the current action.
So in this same slide, so you call it LWR, right? But is that because we're using the fundamental diagram?
Can you repeat your first sentence?
So we're calling this model LWR, right? When you have this squared function, right? But maybe it's the optimal velocity model that we're using here. Or why do we call it LWR? Are you solving the PDE?
So yeah, but because when we try to basically we call it another game interpretation of LWR. We found out LWR can be reformulated in Midfield Game with this function on the right hand side. So the reason is if you minimize f, basically then it becomes u of rho equal to u. So then that's the speed will become the equilibrium speed.
Instantaneously. There's no like time convergence.
Oh yeah, that's another conclusion we found is when we also found out if you use the Midfield Game cost function, but then you shrink your time horizon to very short and myopic, then it becomes LWR. So
but I'm not sure that, so having a model that the speed is given by the fundamental diagram is LWR automatically. It might be another type of car following model in macro. So I'm not sure the term LWR would be, maybe it is, and maybe I'm not getting the idea, but so what do you think about that idea of having a traffic model where the speed is given by the fundamental diagram? that does not make it automatically LWR, right? You need the PDE to make it the conservation law. But I don't think you're solving the conservation law here, right?
Oh, no, we did. So yeah, let me go back to that formulation here. So actually, the Midfield Game composed of two equations. This left-hand side is the flow conservation. Yeah. So yeah, basically this is the
Right.
convergence.
Okay. Yeah, my bad. Yeah, you're right.
Oh no, sorry for not being clear. So that's why we later on we found out seems like a Midfield Game is another traffic flow model.
Yeah.
Yeah, but for people to look more ahead or has anticipating behavior.
Now, I'm not sure if you're familiar with variational theory, but I think it might be related because it's also like a differential game. So you have a variational problem, right? So you minimize the cost function, but it's pretty much similar to what you showed.
Yeah, I'm not an expert in that, but we did look at those literature. I think the concept may be similar, but we didn't find any connection so far. Yeah.
Right, there might be a deeper connection.
Yeah, but the idea wise, I think it's similar.
Excellent. All right. So maybe one more question from the audience. If not, Sharon, thanks again very much for this wonderful presentation. I think it opens the door for what's coming in traffic flow, which is changing so fast. So thanks so much for joining us. Hopefully you'll be able to come to our meetings in the future.
Sure.
And thank you everyone for joining this conference today. Hopefully we'll not have these technical difficulties in the future.
Yeah, thank you everyone, and thank you for having me. I'm so sorry for wasting everybody's time. I know that everyone's busy these days.
It's not your fault, it's Blue Jeans. I think we need to change the platform.
I see, yeah.
All right.
Take care, thank you.
Take care, stay safe.
Bye. You too, bye.